out there as well. So thanks for joining us. As a reminder, please take a time to provide the feedback if you're on the board. So, and with that, go ahead, team 2.
Okay. Good morning, ladies and gentlemen. We are team 2. This team consists of myself, Violet Agadu. I have with me Gerard Wade, Jacob Drake, and Joshua Janowski. And our project for this senior year was about designing a water main distribution for Thomas Farm residential community. A little bit background about this project is about 75 acres of land, which is located in Dewitt Township, Michigan, which is about 14 minutes north of Lansing. It consists of single-family homes, duplexes, and fourplexes, and we are assigned to design a water main system for the proposed site, but other utilities were not considered for the design. We are also sponsored by the Lansing Board of Water and Light. So our site location is northeast of the capital region, looking on the right side of the screen. You could see down there, and you could also see a blown out version of the site, which is at the cross streets of West Clark Road and US 27. You could also see our site from the southwest corner of Myers Road and Solon Road. So we got a proposed layout for the development from the Eastbrook builder, and on the left top corner of the screen is our single family homes, which is also colored in green. At the bottom left corner, we have our fourplexes, and at the bottom right corner, we have our duplexes. So the importance of this project is to ensure that the development has available fire protection flow. It also creates water supply for all the housing units in that development, and it also creates an extension point for other developments that might come into the area. So our design project consisted of a fire flow analysis, a utility plan for all the mains, hydrants, and services for that development, creating a construction estimate, and creating a construction schedule for the project. Some of the constraints associated with this project was lack of connection points, making sure we meet the available fire flow rate, which is 1,500 gallons per minute, and the minimum pressure, which is about 20 psi. We also had to make sure we follow the requirements of BWL about their pipe diameter, the pipe cover, the valve spacing, and the hydrant spacing in that development. So because of the pandemic, we weren't able to do any in-person site investigation, so we had to do a virtual site investigation, and going with that, we used the Eagle Environmental Mapper to see if we could find any historic data that might be useful for our project. And we found that there was no contamination on that site, which was a good thing, so we could proceed with designing the water main system for the project. We also use historic data from BWO to find existing water main systems that we could connect to the new development. With that, I'll be passing off the presentation to Gerard Ray to go through the project designs.
Yes, thank you, Viola. So on your screen, you can see a GIS map of the BWL's existing water main system in the area. So on the top of your screen is located West Clark Road. We have existing 16-inch water main, ductile iron. We have an adjacent site with an 8-inch ductile iron water main existing. And on the bottom right of your screen, you'll see US 27, where another existing 16-inch ductile iron water main will be located. We will be connecting to all 3 of these points, and this will be creating our loop. The software used in our hydraulic analysis was Innovyze InfoWater. This program utilized Hazen Williams and the energy equation to produce its results. As you can see on the screen, here's a verification calculation that we came up with to double check the program's results. Our team, we chose 2 points. We took a flow result from the program. We were able to calculate our head loss and then use the energy equation to determine the pressure at another point, at the second point that we chose. As you can see, the point at pressure 2 was 82.585 pounds per square inch. The software value was 82.444 pounds per square inch. And as you can see, we had about a 0.02% difference in our results. So the assumptions that we made for our designs. First, we assumed that the fire flow demand will be placed on the system during a max flow day. This doing so would allow us to guarantee that our distribution system would be able to provide adequate fire protection to this development during the worst case scenario. Also in our hydraulic, in the Innovyze InfoWater software, the C factors that we placed on our ductile iron water main choice was 120, and for our PVC material choice was 150. Those resemble brand new pipe. We also placed a velocity constraint of 10 feet per second within the model run, and we assumed that the average consumption rate for our residential equivalent units were 300 gallons per day. On this screen, you can see some factors we used to calculate specific REUs for various model homes, and these were used in our hydraulic analysis as well. So on your screen, you can see a layout of our design one. On the right of your screen, you see red that resembles a 16-inch ductile iron water main that extends from the BWO's existing system to the front of our development. You also see another red water main located on the left of your screen that is in Salone Road, that is also a 16-inch ductile iron water main. Throughout the development, you see in green that is 12-inch ductile iron water main. And we chose this diameter and size to guarantee that we would be able to meet those minimal requirements set by the fire marshal as well as our sponsor. So on your screen, these are the results that our model run came up with. We needed to meet a minimum of 1,500 gallons per minute. At a low point in our distribution system, we had approximately 3,500 gallons per minute with the lowest residual pressure of 21.7 pounds per square inch. Another thing we looked at in our design was water quality. We understand that once you reach 24 hours of stagnant water, you'll start to get water quality issues. So we calculated retention time within our distribution system. For this design, we would have a retention time of 19.8 hours with a required occupancy throughout the development of 82.3%. So for our second design, we chose 8-inch ductile iron water main. Now, as you can see on your right and left of your screen, we still have the 16-inch ductile iron water main extensions in the roads. But throughout our development, we have a smaller diameter of 8-inch. This is a cheaper material, and we figured that we will be able to meet our minimum requirements using it. So this slide shows our results. At a low point in our system, we have 1,566 gallons per minute with the lowest residual pressure of 21.67 pounds per square inch. The calculated retention time in this system was 8.9 hours with a required occupancy of 37.2%. Lastly, this is design 3. For this design, we changed the material. We changed to C900 PVC. The diameter is 10 inches, which we went with that diameter because its internal diameter resembled the internal diameter of 8-inch ductile iron water main, and it's a cheaper material as well. So for this design, at a low point in the system, we were able to produce approximately 1,900 gallons per minute with the lowest residual pressure of 21.69 pounds per square inch. The retention time in this distribution system design was 13.8 hours with a required occupancy of 57.5%. With that being said, I will now hand off the presentation to Jacob Drake, who will walk us through the water service design and construction estimate.
Thank you, Gerard. For the water service design for this project, we consulted the Manual of Water Supply Practices, Sizing Water Service Lines, 3rd edition. Since our routing and layout is the same for all 3 designs, the water service also are in common for all of our designs. BWL requires that a minimum 1-inch water service and meter is used in any development in their system. So we started with that as our base for discerning water services. So going through the processes in the 3rd edition, we found that 1-inch was adequate for both the water service and the meter for single homes and duplexes. And 4plexes will receive 2 water services. So essentially they can act as 2 adjoining duplexes, and it therefore works for them as well. For the cost estimation, it includes activities or includes labor, equipment, and material for activities such as trenching, installation of the pipe, as well as installation of our hydrants, valves, and water services. It includes the backfill and compaction after everything is installed, as well as some road repairs because we have to cross West Clark Road on the north side of our development. So we're going to have to tear that up and then replace it when we're all done. For our overhead, we followed BWL's overheads, which is 5% for engineering, 7% for administration. We added a 10% for contingency, as well as an additional 5% for material handling. Here you can see an excerpt of one of our cost estimations. This one is an excerpt from our 8-inch ductile iron design. Here you can see some of the more important aspects of our project, including the installation of the 16-inch main and the 8-inch main, as well as the compacted backfill over both of those main types, as well as the flushing and chlorination of our system before it is tied into the existing BWL system. Here you can see a summary of our total cost for the installation of the water main. This includes overhead and all sub-practices within this part of the process. For design 1, the 12-inch ductile iron, it came out to just over $2.7 million, and we broke that down into linear feet and got about $240 per linear foot. Designs 2 and 3, the 8-inch ductile iron and the C900 PVC, both came out to just over $2.4 million at about $216 per linear foot. For our alternative analysis for this project, we compared the different materials and sizes from our 3 designs. All criteria were weighed equally, and the highest score became our preferred design. As you can see, with a score of 14, the 8-inch ductile iron water main was our preferred design. This is mostly due to its low cost, the preference of BWL to use a material that they're familiar with, as well as it's easier to maintain and sustain than PVC. For our construction schedule, we had to make some assumptions. First of all, we had to pick when we were going to start this project. Since we're going to have some excavation and some compaction, some earthwork, we wanted to make sure that the ground would be there'd be no frost in the ground would be completely thawed. So we picked a start date of April 11th of next year for the start of this project. We used BWL standards for a 5-day work week, no working holidays, and one single man crew. And part of the reason we're only using one crew is because this shows us the longest this project should take from beginning to end. And then also it'd be the most expensive this project would be. So if BWL had an extra crew, they could get this job done faster, but we wanted to show at the longest, what could this project take? I will now turn this over to Josh Janowski to further talk about the construction schedule and the sustainability for our project.
Thanks, Jake. So on the next slide, it shows our construction schedule, and some key things to note is that we sort of divided like the project into 10 different sections, so that when crews finish one section and they're waiting for chlorination, they can begin trenching another section. Another thing to note for this project is that it starts in April and runs all the way till September. On the next slide, you can sort of see a map here showing a progression from north along Clark Road, working south toward Salone. And then some of the tasks that were involved in a section include excavation, laying the pipe, installing valves, hydrants, and services, flushing and chlorinating the pipe, and then backfilling. Another important part of our project was sustainability. One of the ways we considered sustainability was the material. So we considered two types of material: pressure class 350 ductile iron and C900 PVC. For the ductile iron, it has a service life of around 100 years. The BWL is familiar with it, which helps increase longevity. The material is also recyclable. For C900 PVC, it has a service life of 50 to 100 years and can have lower maintenance requirements. Another aspect of sustainability was financial sustainability. When the BWL built a new water main, they planned for it to last for 100 years before it needs replacement. During this time, they can collect fees from residents to help fund projects, maintenance, and expansion of the current system, which makes it self-sustaining. On the next slide, you can see our final design. Some important things to note is that on the outsides, like they mentioned earlier, the 16-inch ductile iron. Throughout the site, you have the 8-inch ductile iron. And if you look at the top right there below the title, you see a green oval. That is a easement, which would help with sustainability if developers wanted to extend west past Myers Road. So in summary, our team was tasked with performing hydraulic analysis, design, construction, scheduling, and estimating for a new development in Dewitt, Michigan. On this project, over 2 miles of 8-inch and 16-inch water main would be placed. 225 residential units would be served. It cost around $2.5 million and would be completed in late 2022. And before we go, there's a few people we have to thank. We'd like to thank our faculty advisors, Dr. Haynes and Dr. Liu. And we'd also like to thank our sponsor from the Lansing Board of Water and Light, Gary Wozniak. Thank you.
Excellent job, Team 2. What do we have for questions from our industry advisory board members?
This is John Polasek. One of the things that the scope of your work was the construction of this thing. Was there any investigation of soils? I'm sure there probably wasn't from the Board of Water and Light, but maybe there was. Because as you know, you run into things that might affect your construction work. Was any of this, and I couldn't tell by, I have a small screen here, so I couldn't tell by the thing. Is any of this, are you moving pavement and putting back pavement at any point of this, or is it all free? I just, and if you haven't done that, don't, just remember that that's all part of a project. So I think it's important to realize that there are a lot of aspects that, when you start trenching and putting back backfill is interesting, and it could run into different issues. So was there any look at your trench that you're digging and the material there?
Yeah, so stated earlier, due to the ongoing pandemic, we weren't actually physically able to go out to the site. We were able to use a resource created by Michigan's Eagle. It was an environmental mapper that it shows historical data of the soil that is in our development. So we didn't see any contamination in this area. So and then if we're talking about the trench, we were forced to, or not forced, since we're operating the BDO system, we have to follow their standards. So as far as backfilling in the trench, we will be using clean class 2 sand, and with some of the on-site material used as backfill over top. The sand will be directly over top of the main, and I'll say for a foot or two, you would have normal backfill from the existing soil on the site.
That was excavated, yeah. Okay. Nice job.
Thank you.
Other questions from our panel?
Comment and a question. So, I mean, overall, all the groups are doing good, but I like how Gerard shows how he used the fundamentals to verify the software output. So you are using the tool with an understanding. So that's a good demonstration. Any consideration, I mean, about the new technologies that they use for construction or replacing these piles, like trenchless technology or something to minimize the disruption? Was there any consideration about? I mean, it may not be available, or I mean, what is the state of the art and how people can use such technologies to minimize the impact damages?
Oh, okay. So as stated, like in the design, we're going to be extending the BDO system along West Clark Road. In order to get to our site, we have to cross that street. So we do have the opportunity to use a directional bore, a directional drill, and drill the water main across the street so that we don't have to tear up the road. But once we got to the site, it's virgin land. It would be cheaper to just open excavate that trench.
Any other questions for team 2?
Yeah, this is Craig Shoemaker, L. Again, I do like you modeled and optimized your water system sizing and did a calculation that was good. What did you do for a detailed cost assessment to get to your $2.5 million construction number? I think I didn't see much detail there.
Yeah, so for the sake of the presentation, we only put a small example from a piece of our detailed estimate. Within our report, it would be a more detailed estimate. For that estimate, we started off using RS means, but we figured it would be more accurate to use data from our sponsor. So from our sponsor, we got productivity rates, material rates, and all that. And we'd use that in our construction estimate.
Okay. And one last question for you, for your modeling, your connection points. How did you get your available pressures and flows at your connection points to start your modeling?
Yeah, so our sponsor, they've worked with I want to say the company is it ArcGIS. They have a GIS map of their whole distribution system that calculates their existing pressures and available flows at points. So I was able to get in, determine that, and then able to model the new development based off those existing points and flows and pressures.
Thank you. You guys did a nice job.
Thank you.
Any other questions for team 2?